So let's first do the first one. Let x be let x be a discrete random variable which takes values from a set S. Then we want to conclude that the entropy of x is at most the log of size of S, which is the entropy of uniform random variable, which chooses the elements in S in a uniform real random. The proof is not difficult. I mean, it's a standard thing that you can imagine. I mean, whenever we have inequality, the first thing we consider is convexity. So if you consider a function which is x log x is convex, then what do we have? So we have, if you consider this entropy, which is summation of negative fx. So convex is like this shape of function, but the negative convex is concave. In here, if you have several points, if you take the average, then that lies below of the, taking f of the average. So you take the, so this is average, then you take the f of the average. What's the average of this? This sums up to 1, and there are s many, so average is this. So this is the case, but you multiply size of s on both sides and you get this. Then what do we get? So what's this? This is nothing but 1 over s times log 2 1 over s. And you multiply this, and then you multiply negative, then this is log 2 of size of s. So which proves the lemma. So now we accomplished first one. And in order to be able to add the information, we consider, we define adding, and we try to come up with some concept which can measure the common information. So when there are two random variables which may be or may not be independent, so not necessarily independent, we let G be x, y be the joint random variable. So for example, if you have a number a from bracket n, x, so which is chosen, say, uniformly random, x is the a mod, say, 6, y is a mod 8. Then what do we get? Let's say this is 48. Then a could be taking values from 1 to 5 with the probability 1 over 8, 1 over 8, 1 over 6, and 1 over 6. X. Y can take the values from 0 to 7 with the probability 1 over 8, 1 over 8. But x, y could take a value. We can. So for example, it would never take a value which is, say, 2, 1. So it could take a value like 1, 1, 1, 2, 2, and yeah, I mean, anyway, so in this case, so this is not necessarily, I mean, chosen uniformly at random or anything. So because they are, I mean, dependent, some of the values cannot occur, and some of the value can occur with a higher probability, and that can happen. So maybe I could come up with a better example. Let's say 2. Then y is 0 or 1 with probability half and half. Then 1, 2, 3, 4, 5, 0. Say 0, 0, 1, 1, 2, 0, 3, 1, 4, 0, 5, 1. Each of these happens with a probability 1/6. But the other 6 values like 0, 1 or 2, 1, 0, and so on, those never happen. On the other hand, if x and y takes the value 0 to 5 with probability 1/6, and this takes value 0, 1, probability 1/2, if they are independent, then all 12 value 0, 0 to say 5, 1, there are 12 values, all of them occurs with the probability 1/12. So this joint distribution can be different one if x and y are dependent in different way. So, and we write hxy be the entropy of this G, which is joint distribution. Then we know this subadditivity, which says that for given random variable x and y, which takes values in S and T, say we have that if you consider the joint distribution, joint random variable x and y, then the information it carries is at least as large as x, and at most as large as the information together. So as I mentioned before, x carries this much of information and y carries this much information. Some of the partial information that y carries could be already known, so we must have this. So, and also, even if y doesn't give anything else, anything new, still the information that we have should be at least as large as x alone. So for x and y, we write p x be the probability that say x is x, and py is the probability that y is y, and pxy is the probability that x is x, y is y. Then what's entropy of x, y? This is by definition, you consider all x, y, and you consider the probability x and y happen times log 2 of probability x, y happen. Then, what do we know is that the probability of x, y happen is at most the probability of x happens. So this is joint event. And if you take the log, And if we take the minus, then the inequality is the other way around. So we know that this is, you consider all x and y, probability of x comma y log px. So then this is actually smaller than equal to this. So this is smaller than equal to that. But here, what do we know? If we fix x, so this is nothing but summation of x, summation of y. But if you fix x, then here, so this is just a constant. So we can write it this way. But what's this? This is nothing but px, which is entropy of x. So this shows that our definition of entropy works as we wish it in our intuition of treating it as an information. Also, in order to show the second inequality, we measure this. So what's this? You can, again, using the definition, then this is minus pxy log px minus pxy log py minus plus pxy log pxy. So this is summation of x, px, log px minus, right? But you can add this as a, because px is same as for all y, pxy. If you add this events probability together, then you get this. So you can further divide it into pxy. So that's how you get this. And same way, entropy of y can be written here, and entropy of xy can be written in this way. Then this is summation of x comma y. Here we can write it as a pxy log px times py over pxy minus. Is it correct? So here, okay. This is the simple property of log. Now let f of g be g times log sub 2g. And let's write gxy be the pxy over px times py. Then what do you get? If you use the convexity, give me a moment. What was the let me check something on my calculation. Yeah. So then let's say we have this. you can write this as a summation of px, py times gxy and log gxy. So this minus, you can flip this to yes. Okay. So this is, what it is, and you can rewrite this as p x py gx and f of gxy. And again, this f is convex. So again, convex, you take the average of value, then that's higher than the average of function value is higher than the function applied to the average. So this is this sums up to 1. So this is average of function value, which is higher than, you average it and applying the function. And what's this? This can be rewritten as a pxy over px times py. So this and this cancels out, and this sums up to 1. So this is f1, which is 0. So we have this at least 0, which gives us this inequality. So this lemma is proved. So we know this, but we want to now measure the difference. How much of the information y carries were already known by x? So our intuition is that the information that xy knows gives, and you subtract, say, okay, you know y, and then let's swap the order. You already know y, and you want to measure how much information x additionally give. So our intuition is that that should be this. The information xy together gives minus the information that we already had, which come from y. But we don't want to take this as a definition, because moreover, we can take the following definition. So it's really up to a choice. You can actually choose this as a definition or the other one as a definition, but let's define it the other way. Let's say for an event E, let entropy of x given E, with you take the whole summation of the probability that x is actually x, conditioning E, and you take the probability that x is x, again conditioning E. So this is nothing but the same definition as of the entropy, but we add the conditioning. So inside of this smaller space, you compute the entropy, then this is this. And now what? Y give us some information and x give us additional information, and we want to measure this. That means once y is given, the entire probability space is shrinked into a subspace, which is E. And there we want to measure how much further it can shrink by x. But there are two randomness here. First is that depending on what event in y happened, the shrinking can be taken differently. And then after that, which value x take might be shrinking it in a different way. But the second one, so in order to average it out, we actually, come up with this formula to measure the average information that we get. So again, we can consider this conditional entropy of X condition on Y is that expected entropy when Y is given. So assume Y is given with Y, then this is an event. And that event shrink the probability space. And assuming that, we measure how much X shrink. And we average out with for all Y. Then this is a kind of expected additional the number of bits of information that we get from X, knowing Y. You can again write this as Y, probability of Y being Y, times this H, X, Y being Y, which can be written in this way. So this is, say, negative here, summation of X, probability that X is X, assuming Y is Y, log 2, probability that X is X, Y is Y. So this, and you can actually, this together, if you multiply, that's X is X, Y is Y. So you can write down the formula for this. Then we want to check that this actually gives the same number as this. As our intuition tells you that the additional information we get from X and Y on top of Y must be this. So this is called chain rule for two discrete random variable X and Y. The conditional entropy that we define here is actually same with the additional information we get from X and Y on top of, compared to Y. So as we have probability of X equal X, assuming Y equal Y, is Pxy over Py. So we use the same notation as before, probability of the X being X, Y being Y, the capital X being small x, capital Y being small y. Then what we have? The conditional entropy is expected entropy we get from X, and that's minus Py, summation of X, probability that X is X, Y is Y, conditioning on log. So this is what we get. Then what do we get? So this is first, you can change it into Pxy over Py. Then that's summation of, say, xy. This times this is nothing but minus, p times, p sub xy. And the above part is log 2 pxy. So log, this is same as log pxy minus log py. And you add the summation of xy, pxy, log py. So this is what we get. And what's this? This is xy, entropy of xy, plus y times py log 2 py. So this is what we have. And here, okay, if you just write it down by word, this is what we have. But this you can write it as a summation of y, summation of x, pxy, because this part is belong to, depending on x, this doesn't belong to x. So this is what we have. And what's this? This is nothing but the py. So we can write this as this. That's exactly same as we want. So this conditional entropy is exactly the additional information we get from x and y on top of the information that we already have from y. And okay. And let's prove one more lemma before we actually finishing today's lecture. So dropping condition. So for discrete random variables x, y, g, what we have is that the conditional entropy. So additional information we get from x when we already know x, y, and g is at most the additional information we get from x when we only know y. So y is known and g is known. X give us new information. And when we know y, the new information we get from x is this part. But when we know y and g, the additional information we get is this part. So this is small. So this is also intuitive. But so I'm keep talking about this is the information we get, the number of bits of information we get. But that's our intuition. Our actual definition of H was this formula. So we have to actually keep checking this lemma so that our definition actually is a correct definition, which means that this actually is representing the number of bits of information that we get. So these lemmas are all like a kind of proof that our definition is the correct definition, because it satisfies all the information that we intuitively then must, the correct parameter which measures the number of bits of information must also satisfy, this kind of lemmas. And as we already show that this conditional entropy of x conditioning on y is you add the entropy of joint information minus entropy of y. And by the previous, lemma, this joint information is at most the entropy of x plus entropy of y, and this gives us the entropy of x. So this is known. Then what we want to now compare this and this. So you add some condition. So here we have a condition, we can delete it. So now we have two conditions and we can delete one condition by the same logic. Then we get this inequality, which proves this dropping condition lemma. So, yeah. So we define the entropy, and later, we will see some examples that we actually use this to solve some combinatorial problems.